So this video is going to be looking at core practicals 5 and 6 for the Edexcel IAS chemistry course. We're going to be looking at the organic core practicals, so all of them coming from topic 10. So the first core practical is number 5, which is the hydrolysis of halogenoalkanes. So you can find more information about the theory behind this on the halogenoalkanes video, which is available on the YouTube channel. So the objective of this particular experiment is to investigate the relative rates of the hydrolysis of primary, secondary and tertiary halogenoalkanes, as well as chloro, bromo and iodoalkanes. So just a reminder, a primary halogenoalkane is going to have one R group attached, so we may get something like that would be a primary halogenoalkane. A secondary halogenoalkane is going to have two alkyl groups. So we may have something like that for secondary. And a tertiary is going to have three alkyl groups. Where we may get something like that. Now, each halogenoalkane will form a precipitate when it reacts with silver nitrate. That is how we test for halides. And the formation of the precipitate will be at a different rate for each halogenoalkane, and that's what we can use to determine which one is going to hydrolyze fastest. So what apparatus do we need? Well, first of all, we need all of our halogenoalkanes. So we're going to be using 1 chloro, 1 bromo, and 1 iodobutane. So that's comparing change in the halogen. And then we're also going to be using 2 bromobutane and 2 bromo 2-methylpropane, and that's my primary, secondary and tertiary. Of course, I'm going to need my silver nitrate solution. I'm also going to need some ethanol, as well as some pipettes, a measuring cylinder, conical flasks, test tubes, and of course stop clock. With regards to safety, as usual, we need to have our eye protection and make sure we're wearing suitable chemical resistant gloves. We don't want to touch any of our reactants or products, but there's also two others that are very important here. So there cannot be any open flames in the vicinity, as the halogenoalkanes and the ethanol are both extremely flammable. The lab also needs to be very well ventilated so that we don't have any fumes being inhaled, because some of these can cause some damage. So how do we do this experiment? Well, first of all, we need to set up a water bath, and we want it to be around about 50 degrees Celsius. I take 3 test tubes and I add 5 centimeters cubed of ethanol to each test tube. I then want to add iodobutane to the first test tube, bromobutane to the second, and chlorobutane to the third. I then want to loosely place a bung into the test tube and then place it into the water bath. That will then allow it to come to the correct temperature. I then want to take another 3 test tubes and I want to put 5 centimeters cubed of the silver nitrate solution, and I put it all into the water bath. I leave it for maybe about 5-10 minutes just in order to allow them to all come to 50 degrees Celsius, and when they've reached that temperature, I take a silver nitrate test tube and I add it to the iodobutane first of all, and then I time how long it takes for the precipitate to form. I then do the same with the bromo and then the chloro, so that I have 3 times. 1 for the bromo, 1 for the chloro, and 1 for the iodo. I then repeat all of these steps, this time using the primary, secondary and tertiary halogenoalkanes. So this is a fairly simple experiment in terms of how we actually carry it out. Now, this is a nucleophilic substitution reaction, and typically the water would be acting as a nucleophile, and we call it hydrolysis. Because we're wanting to make sure that we have a good mixing of our products, we want to use ethanol instead of water, so we want to make it an ethanolic solution instead of aqueous. And we use our silver nitrate so that we can see the reaction happening and we can time the formation of that precipitate. And the formation you can see is written in the equation here. So we have the halogenoalkane being broken down into an alcohol, and then our halogen being freed. That halogen then reacts with the silver and then forms our precipitate. So the things that we control are either the halide or the type of alkane, halogenoalkane, the type either primary, secondary or tertiary. So that's the one thing that we are going to change in each of our reactions. So if we start off with the comparing chloro, bromo and iodo, what we should see happening is that the chloroalkane is going to have its white precipitate forming very slowly. Notice that it is white for chloroalkanes. For the bromoalkane, we're going to get a cream precipitate. It's going to be in the centre, so that's going to be the third fastest. This is going to be the second, and for iodo, we're going to get a yellow precipitate, and it is going to be the fastest precipitate formed. Now, the reason for this, again, we go into more detail about this in the halogenoalkanes video, but just to summarise, it's all to do with the relative strength of the carbon-halogen bond. The carbon-iodine bond is the weakest one, therefore it is the easiest to break. So because it is the easiest to break, then the precipitate is going to form very quickly. The carbon-chlorine bond is much stronger, and it is the strongest of the three. So because it is the strongest, then the precipitate is going to form the slowest. We don't even look at carbon fluorine because that bond is far too strong and we wouldn't see a measurable result. When I have my primary, secondary and tertiary halogenoalkanes, what we should see is that the tertiary is the fastest, followed by the secondary, followed by the primary. Now, the good thing is at IAS level, we do not need to understand the trend in this topic. We just simply need to know the trend, that it goes from fastest at tertiary to slowest at primary. The reasons for this is it requires a deeper understanding of the actual mechanism. This will be covered in topic 11 when you get into year 13. So some errors that may come up in this particular reaction, well, it's sometimes making sure that your water bath is at the correct temperature, and we use that to control the temperature of the halogenoalkane. If we use a lower temperature, we're going to reduce the rate of the reaction, and that gives us a larger time difference between the halogenoalkanes. It takes longer for the experiment to happen, but the good thing is it gives us a lower uncertainty in terms of the accuracy. So sometimes it's nice to find a good balance in the terms of the temperature that we want to use. So that's why we use 50. It's not quite room temperature, but it's not boiling and it's not too warm. It's just a nice warm temperature to allow the rate of reaction to happen at a suitable time, but there's still a big enough difference between our different halogenoalkanes to see the reaction. Now, there's not many past paper questions, if any, on the actual practical side of this. This will tend to come up in Unit 2 more often than not, because it's actually, we'll be asking about the process of the formation of the precipitate and what the ionic equation could be. Now, it could come up in the new specification. Remember, most of the past papers you'll be covering will be the old spec, but the majority of the content of this, I think, will come up in Unit 2. So let's move on to Core Practical 6. Core Practical 6 is the chlorination of 2-methyl-propan-2-ol. And again, this is in topic 10, focusing on the halogenoalkanes and the alcohols. So the objective of this reaction is to produce and purify a sample of 2-chloro-2-methylpropane. So the halogenoalkanes can be formed from alcohols by replacing the OH group with a halogen. Now, primary and secondary alcohols form chloroalkanes when we react them with phosphorus chloride, whereas tertiary alcohols, they will be reacted with concentrated hydrochloric acid. Any organic compound that we form should undergo a purification process, and you can find more information about the purification process in the alcohols video, which is available on this YouTube channel. In order to purify, we're going to use a separating funnel, distillation, and a drying agent. And we're going to go through how we do this, and we'll also look at a past paper question for this. So in terms of the apparatus that we need, you can see that it's quite a sizable list, so I'm not going to go through everything. I'm just going to point out a couple of key points, and that would be we use distillation apparatus. We're going to need our separating funnel. We have our 2-methyl-propan-2-ol. So if we can't remember what that's going to look like, notice that it is a tertiary alcohol. So because it is a tertiary alcohol, we are going to be using hydrochloric acid in order to react this. And we're also going to need to use calcium chloride as well as sodium sulfate. And I'll explain as we go through what we use these for. So in terms of safety, there are again quite a few safety rules here. So we need to do this in a working fume cupboard. The reason for that is it does give off vapours that are particularly toxic, and we don't want them to be inhaled by anyone, especially not if you have a respiratory problem. As normal, we want to make sure we have eye protection, and we want to avoid any skin contact with our reactants or products. And lastly, this is a flammable liquid, so we want to make sure that there are no open flames. So the first part of the method is going to be using our separating funnel and the actual reaction between the hydrochloric acid. So the first thing that we do is we take our alcohol and we add our concentrated hydrochloric acid and we put it into a large conical flask and then we swirl it. We place a bung into the mouth of the flask and we continue to swirl, and every so often we're going to remove the bung in order to release the pressure. We do this for about 20 minutes until we start to see 2 layers appearing. Now that is very, very important. We're then going to add 6 grams approximately of anhydrous calcium chloride, and we're going to swirl that until all of it is dissolved. What this does is it makes sure that any unreacted alcohol, so any alcohol that has not become our halogenoalkane, will go into the bottom aqueous layer and not into the organic layer. This organic layer is where we have our desired product. Okay, so by adding this calcium chloride, what we're doing is we're increasing the density of the aqueous layer, and we're going to be having the alcohol more likely being attracted into the aqueous layer, and then we can easily separate the two. We separate them using a separating funnel. We transferred all of the liquid in, and then we allow it to settle into its 2 layers. We run off and we discard the lower layer because that's going to be our aqueous layer, and we want to keep the upper organic layer. The organic layer will typically have a lower density than the aqueous layer, so which is why it will go on top. But we're not quite finished. What we now need to do is we need to add sodium hydrogen carbonate to the separating funnel, and we swirl it again, making sure to release the bung so that we give off any pressure. Okay, and again we run off and discard the lower aqueous layer, and we repeat this process, again discarding any aqueous layer. We then want to run off the organic layer into a small conical flask, and we're going to add this anhydrous sodium sulfate. This is our washing section. And what we should see is the mixture is a bit cloudy before we add the sodium sulfate, and then we swirl it and we leave it until the mixture is completely clear. Once we've done that and we've got our clear liquid, we're going to decant the organic liquid into a pear-shaped flask, and then we're going to distill our product. We distill it using fractional distillation, and we want to collect the fraction that is between 50 to 52 degrees Celsius. And then we can analyse the sample by adding 5 centimetres cubed of ethanol and sodium hydroxide into a warm water bath, and then adding our nitric acid and our silver nitrate and record the observations. And that is making sure that we can test for our halide. Now, of course, we don't want to use our entire sample for that. We're just going to analyse a very small part of it, and we should see a precipitate being formed when we add the silver nitrate of our silver chloride. So a few key points of how this works. Well, we use a weak base when we react this so that we don't get a hydrolysis of the halogenoalkane. So that's if we go back where sodium hydrogen carbonate is the base that we add. If we were to use sodium hydroxide, we're going to get a reaction happening via nucleophilic substitution, and we don't want that happening. The equation for the reaction, you can see here, we have our 2-methyl our tertiary alcohol reacting with the hydrochloric acid to make our tertiary halogenoalkane. Now, the one thing that we do need to be aware of, and one thing that can cause an error, is that sometimes we may lose some of our products when we're transferring our liquids between the different vessels. So when we're trying to work out a percentage yield, we just have to make sure that we do realise that we may have lost some of our products. So we would have an accuracy or a percentage error in this calculation. So let's finish off by looking at a past paper question. This is from the January 2018 paper, and it is pretty much the exact same process that we've just went through. So how we can convert 2-chloro-2-methyl propane from 2-methyl-propan-2-ol, and it goes through the different steps, and it also gives us some data about the molar mass and about the density. So the first question is asking for hazards of each of the reactants. Looking at the alcohol and the concentrated hydrochloric acid. So if we start off with the alcohol, the most important thing is that we are aware that it is flammable. Now, the question does not ask us about how we reduce the risk, we just have to state what the actual risk is, or what the actual hazard is. So that it is flammable. For the concentrated hydrochloric acid, that is very corrosive, which is why we, of course, wear gloves. So step one, so just to go back to step one, we're mixing our alcohol and our hydrochloric acid into the conical flask, which is stoppered and shaken, and then we release the pressure. So part B is asking, well, how do we release the pressure? And it is very simply, we remove the stopper at intervals. And that just allows any pressure that builds up in order to be removed. Now, part C is asking why we have to release the pressure in step one, even though we're not actually forming a gas. Now, the important thing to remember with these particular molecules is that they are all very volatile. So they are very easily vaporized and put into a gas. So we do need to take that into account, that if we just leave the bung on and we have this volatile reaction happening and we're forming this gas, we could either smash the flask, the stopper could pop out, we could have an expansion happening, but the easiest way is just simply to say to release any volatile compounds. And that stops any smashing or any breaking or any damage to our flask. So you can see that I've kept the question on the left-hand side, and then we're going to look at part D. So the purpose of adding the sodium chloride in step 2. So step 2, we add the sodium chloride to the flask, and once it is dissolved, we then transfer it to the separating funnel. Well, adding the sodium chloride has a very specific purpose, and it is very simple, and it helps with better separation. And the reason for that is because we are increasing the density of the aqueous layer. So it just allows us to get a better separation. So you can see that the density of the aqueous solutions is about 1.2. If we add in the sodium chloride, we're going to get an even higher density, and then it makes it easier to separate from the other two. Part A is drawing a diagram of the separating funnel and the contents in step 3 and labelling each layer. So we know that we're going to have an aqueous layer and an organic layer. So we get 2 marks here. The first mark is to actually draw the separating funnel. So we can draw a funnel of any shape, just making sure that we have a narrow top and then a tap at the bottom and a narrowing at the bottom. That would get you your first mark. And then the second mark is looking for the layers. You can show the bung, but you do not have to. It's probably good practice to show it. The second mark is showing of the layers. So we have 2 layers here, and of course we have to make sure that we label them. So our top layer is our organic layer because it has the lower density, and the bottom layer is our aqueous layer because it has the higher density. So for part F, suggest what you would see after the anhydrous sodium sulfate has been shaken with the mixture. Well, we know that this is a washing process, and we've previously said that we should see our solution turning clear. And that's how we know that it has been washed and we've removed all of those possible impurities. Part G is then looking for a suitable range to collect the product in step 4, so during our distillation. We're saying that the boiling temperature of 2-chloro-2-methyl-propanol is 51 degrees. So we want to have any close range that covers 51. So the easy is to have 50 degrees to 52 degrees. We want to make sure it's a very, very small range that we're going to be collecting our product between. And then part H, a 4-mark question on calculating the mass of 2-chloro-2-methylpropane that is produced if the yield is 85%. Well, the first thing that we need to figure out is what is the mass of the alcohol that we use. So we're going to need the fact that we use 20 centimetres cubed of it, and we're also going to need to use the density. The density is in grams per centimetre cubed. So if I want to work out how many grams I have, I do my density, which is 0.789, and I multiply it by my volume that I used, which is 20, which gives me 15.78 grams. I can then work out the number of moles of the alcohol, which is going to be 15.78 divided by its molar mass, which we're given in the table as 74.1, and we get an answer of 0.21296 moles. These are in a 1-to-1 ratio, so that's going to be my number of moles of my 2-chloro-2-methylpropane. So I can then work out my mass of my product, which is going to be my number of moles, multiplied by my molar mass, which is 92.6. So I should get a theoretical mass of 19.720. But remember, our question says that our yield is only 85%, so our actual mass is 85% times 19.720, and that gives you an answer of 16.762 grams. Now you can see that I've included the answers to all of our past paper questions, so you can go through and you can check through them if you are trying these in your own time. That's everything for core practicals 5 and 6. Hopefully everything in this video has made sense, but if you do have any questions, please feel free to leave a comment, and we hope to see you back on the channel in future for more videos.